If you look at the raw spread of the Milky Way, you see billions of stars burning in complete chaos. To figure out how they all actually relate to one another, astronomers rely on a master map. This chart is the Hertzsprung-Russell diagram. It categorizes every known star by two simple metrics: its total brightness on the vertical axis and its surface heat on the horizontal axis. Notice that most stars fall right into that central diagonal band. A star's location here is not random. Strict thermodynamic laws dictate exactly how a star evolves. When they expand and cool, they shift predictably into those upper right clusters of giants and supergiants. This strict predictability provides a definitive baseline. When something appears to occupy an impossible position on this map, it highlights an object that isn't behaving like a normal star. A Dyson sphere is a theoretical alien megastructure built to completely enclose a star. The engineering goal is to capture 100% of that star's energy output. Physicist Freeman Dyson proposed searching for these massive enclosures back in 1960. He realized they present a unique observational problem. If an advanced civilization successfully builds a shell that traps all of a star's light, that star vanishes from standard optical telescopes. The visible light never reaches us. To find the most advanced civilizations, we cannot look for starlight. We have to look for the invisible thermal footprint left behind by the machine itself. From an engineering perspective, building a giant sphere around a massive, violently unstable star wastes an enormous amount of resources. If you want to build a permanent energy harvesting shell, there are really only two logical host candidates: red M-dwarfs and white dwarfs. Red M-dwarfs make up about 70% of our galaxy. They are incredibly stable and burn for trillions of years, offering an essentially permanent power supply. White dwarfs offer a different structural advantage. They are highly compact stellar remnants, often just a fraction of our sun's size, requiring a much smaller sphere and less material. Applying this engineering logic shrinks our search area. We can ignore massive, chaotic giant stars and focus our instruments purely on small, stable dwarfs. Even an alien megastructure cannot break the laws of thermodynamics. Any energy a Dyson sphere absorbs from its host star eventually has to be radiated out into space as waste heat. As the sphere gets larger in radius, its surface temperature drops, but the total amount of energy it radiates remains identical to the original star inside it. This diagram shows the resulting Dyson shift. By blocking visible starlight and emitting only infrared heat, the object drops completely out of the natural stellar sequence. It settles into an isolated low-temperature void, glowing steadily between 50 and 300 Kelvin. This shift creates a clear thermal signature that separates the artificial from the natural. We now have a precise range on the infrared spectrum to monitor. Among all possible targets, white dwarfs are the absolute cleanest environments for this kind of observation. They cool down at a highly predictable rate and almost never have natural warm dust clouds hanging around them to confuse our readings. This graph illustrates the exact visual flag we are looking for. A natural white dwarf creates a smooth downward curve. If a Dyson sphere is present, we would see a massive smooth spike interrupting that baseline right in the 10 to 60 micrometer range. Natural debris, like crushed asteroids, leaves a very specific, jagged chemical fingerprint made of silicate rock. A perfectly smooth spike proves the object is a solid shell. Because white dwarfs are naturally so quiet in the infrared, a severe heat spike stands out clearly against the empty background. It is one of the strongest possible indicators of a constructed object. We finally have the hardware capable of executing this search. Modern observatories like the James Webb Space Telescope and the WISE mission are highly sensitive to those exact mid-infrared wavelengths predicted by the math. Astronomers are currently cross-referencing massive catalogs of nearby dwarf stars, filtering millions of data points to find the tiny fraction that glow unnaturally between 50 and 300 Kelvin. We are no longer sweeping the sky hoping to catch a stray radio signal. We are running a calculated search for the impossible shadows resting on astronomy's master map.